there. Today we're going to be looking at section 6.5a. We're going to be starting to look at the trigonometric form of a complex number. So usually when we've stated complex numbers, we've written them in what we called standard form, a plus bi. And so in this section, we often refer to complex numbers as z, okay? So when we have the z is just going to be a complex number, a plus bi. So it can be represented on a 2D complex plane as a specific ordered pair, a comma b. So what we do is we use what we are familiar with as an axis, but our x-axis represents the real axis, and then the y-axis is going to be our imaginary axis, okay? And this is considered then the complex plane. The Cartesian plane is what we usually use, the xy coordinate system, but this is considered the complex plane. So let's take this example where we're just going to plot the complex number z, and that's 2 minus 3i. So again, this 2 is the real part, and this negative 3i is the imaginary part. So on our complex plane, that's going to be like plotting the point 2, negative 3. Okay? So we would just go over on the real axis 2, and on the imaginary negative 3, plot a point right here, and that, my friends, is where 2 minus 3i is. Okay? Another thing that we look at often is the absolute value of a complex number. When we have the absolute value of a complex number, so the absolute value of a plus bi is just given as the square root of a squared plus b squared. In all intents and purposes, that's the distance between the origin and then the specific point that you plotted. So let's find the absolute value of z from our first example. So remember, our z was 2 minus 3i. So to find the absolute value, we're going to take the real coefficient and square it. And we're going to take b, not bi, but just the b, the coefficient, the y, what we would think is the y part that we plotted, and square it. And then take the square root. So I have 4 plus 9. So then that's going to equal the square root of 13. And so that is going to be our absolute value of z. Our absolute value of z is going to be the square root of 13. Okay. So we've mentioned a little bit about what polar form is. And again, we'll talk more about polar form when we get to chapter 9. But we're going to look at what the trigonometric form of a complex number would be. And again, this is going to be the idea of polar form. So I want us to think about a specific point, AB, okay? That's, again, in our complex plane. So this would be our real axis, and this would be our imaginary axis, okay? And you can put the point anywhere, okay? And so this is going to be that point AB that represents the placement of that complex number C, okay? What we are going to have is we are going to look to see at, like, kind of think about, I guess I'll say like a circle, and we'll think about it this way. And around where that point is, and I'm probably not going to do a very good job drawing this circle. Okay, but let's think about a circle this way. And if we call this R, for example, I can drop this down, and I know that to get from here to here is going to be A, here to here is going to be B, okay? The other thing I want to notice, you to notice, is where that lands. So this is going to be a specific number of degrees or radians theta away from that real axis, okay? So when we find the trigonometric form of a complex number, this z equals a plus bi, what it's defined as is we can say r times the cosine of theta plus r times the sine of theta I. Because when we're looking at that, and I know right now that our theta is here, but if we're looking at that, as far as that goes, that will give us our A and our B value. Like if we consider what the cosine of theta would be, our cosine of theta would be A over R. And again, like this, I guess you could think about it as like theta prime, okay? But our cosine would be A over R. So R times A over R would just be A. And the sine of this little theta would be B over R. So R times B over R would just be BI. So that's where that idea comes from, okay? And so oftentimes we'll write it like this instead. We'll like factor out the R and we'll have it as R times the quantity cosine theta plus I sine theta. Well, and that's the other thing, is usually we write the I in front. So let me fix that, sorry. Just so that we know that we're not taking the sine of theta times I that way, okay? And again, in this case, this is where A equals R cosine theta, and B is going to be R times the sine of theta, okay? And when we think about what R is that distance from the origin to that specific point. So we know that our R is really like our absolute value of Z, which above we said was going to be the square root of A squared plus B squared. And then when we are thinking about theta, when we think about, we usually use tangent for that because we'll know what A and B are very easily. So our tangent would be opposite over adjacent. So our tangent of theta is going to be B over A, but make sure that you're careful about what quadrant it lies in, okay? And your theta can be in either degrees or in radians, it doesn't matter. In a quiz test situation, of course, I would tell you what one I would want in a specific case. So we can see that the things that we really want in this case are, we need two things. We need R and we need theta. And so those are going to be the important pieces that we have here. When we talk about R, sometimes R is called the modulus of Z. I don't think I use that very often. And then this theta is often called the argument of Z. But that's kind of the idea, like where the idea of the trigonometric form of the complex number occurs from. It's that idea of kind of like drawing a triangle in there and looking at those trigonometric relationships, okay? So what you guys will want to be able to do is to take a number, a complex number, and to write it in trigonometric form, okay? So let's practice that in example 3. It wants us to find the trigonometric form of the complex number. Well, again, we need two things. We need R and we need theta. So R shouldn't be too bad. Our R, remember, is like the absolute value of Z, which we said is going to be the square root of A squared plus B squared. So that gives me the square root of 1 plus 3, which is the square root of 4, which is 2. That's super pretty. It's not always pretty, but in this case, it's really nice. Okay. So now let's look for theta. We're going to say that the tangent of theta is going to be B over A. So that's telling us that the tangent of theta is the opposite of root 3, okay? We're lucky in this case because this is on the unit circle, right? And because it's on the unit circle, we won't have to use a calculator and like use the inverse tangent or anything like that. But we want to think about what quadrant this is going to lie in, because remember that the tangent could be -√3 in quadrant 2 or in quadrant 4. So let's see where this actually lands. If I think about plotting this, -1√3 is going to be in quadrant 2. So we know it's going to be on the unit circle in quadrant 2. And so in that case, we know that that is going to be 2π3 because it's in that tall triangle family. Okay. So now we have r and we have theta, so we're ready to write our complex number. So we're just going to say that z equals 2 times the cosine of 2π3 plus I times the sine of 2π3. And that's it. So in these cases, all we have to do is find r and find theta, and then we're golden. Okay. In letter B, this one's a little too similar, but that's okay. In letter B, we have that z is -2 times 1 plus √3i. I would just rewrite that as -2 plus 2√3. Oops, it would be minus because if I distribute the negative. -2 minus 2√3i. I don't know why they write it like that sometimes. But anyway, so we can use this. And again, our goal is to find r and theta. So if I find my r value, my r is again going to be like the absolute value of z, which is going to be the square root of a squared plus b squared. And if I find that, -2 squared would be 4. -2√3 squared would be 4 times 3, so plus 12. So that's the square root of 16, which is 4. So another pretty r value for us. Okay. And now we'll find theta by using the tangent of theta equals b over a. So these cancel, and this ends up being +√3. So once again, this is nice because this is on the unit circle, so we don't have to use our calculator. But we want to know what quadrant it's in, because tangent could be +√3 in either quadrant 1 or 3. And if we think about where this guy is going to land, -2, -2√3, this is going to be in quadrant 3. So again, we want the tall triangle family in quadrant 3, so that means that my theta is going to be 4π3. Okay. So when I write my complex number in trigonometric form, I have 4, and then I'm going to take the cosine of 4π3 plus I times the sine of 4π3. And that's it. So that's really the secret there, is we just use the complex number to find r, we find theta, and then we put it in that form. And that's our polar form or our trigonometric form. One thing about the homework, don't worry about graphing the complex number. I know I have it like in a little sketch here. I don't need you guys to graph the complex number, just find the, like beautifully, just use that to find the quadrant and find the trig form of the complex number, okay? Sorry, this is like stuck. Okay. Now we also want to be able to go the other way. In these questions, we have something that's in trigonometric or polar form. And what we want to do is we want to write the complex number in standard form. And when we talk about standard form, that's when we have that a plus bi form that we're so used to, okay? One thing to do is just to evaluate, to be honest with you. And in number 5, what we're able to do is we are able to find what the cosine of 7π6 and the sine of 7π6 is, because those are on the unit circle. So what we can do is just evaluate each of those. So if I take the cosine of 7 pi 6, again, that's the small triangle family. So that's going to be root 3 over 2. 7 pi 6 is going to be in quadrant 3. Okay, and so cosine will be negative in quadrant 3. Okay. And now I have I times the sine of 7 pi 6. So 7 pi 6, again, is the small triangle family. So that's going to be 1/2. And in quadrant 3, sine is also negative. So if I distribute that, that just gives me negative 5 root 3 over 2. And then minus 5 over 2i. And that's it. Okay. Now, if I'm looking at letter B, I can do the same thing, except I'm not sure what the heck the cosine of 230 degrees and 30 minutes is, or the sine for that matter. So here's a question where you would just use your calculator to help us out. Okay, so I know that 30 minutes is 1/2 a degree. So I'm going to make sure I'm in degree mode. Okay, looking good. And I'm just going to take 6 times the cosine of 230.5, essentially, because that's really all that is. So again, I'm just going to distribute here. And that gives me about negative 3.816. And now I'm going to take 6 times the sine of 230.5 degrees. And that's going to give me negative 4.630 if I round to the nearest thousandth I. Okay. And I'm going to keep the approximately there so people know that I rounded. Okay. But really, that's all you have to do to go the other way. Okay, is just evaluate. Now again, if it's on the unit circle, make sure it's exact. But if not, you can just use your calculator to help. Once again, in these questions, don't worry about graphing the complex number, just find the standard form. Okay. So in addition to going back and forth, we're also going to look at how to multiply and divide complex numbers. Okay. So we're going to have these two complex numbers, and we're going to have them in this trigonometric form, in this polar form. Okay. So when we have z1 times z2, the way that we can multiply those together is that we can take the two moduli, r1 and r2, and multiply those together. And then we can take the two arguments, theta 1 and theta 2, and add them together. Okay. So again, in this case, what we do is we multiply the moduli. I think there are two i's. No. And then we add the arguments. Okay. So let's take a look at that in example 5a. It says perform the operations, and it just says to leave the result in trig form. Okay. So in the trig form, that means that it's in this specific form. So we have two complex numbers that we have here. We have this 3/2 times cosine pi 6 plus I times the sine of pi 6. And we have 6 times cosine of pi 4 plus I times the sine of pi 4. Okay, so those are the two complex numbers that we are multiplying together. So we would want to start by multiplying the two moduli. Our moduli here are the 3/2 and the 6. Now we want to add the arguments. So we're going to have the cosine of pi 6 plus pi 4 plus I times the sine of pi 6 plus pi 4. So to add the fractions together, you might want to make a common denominator. So a common denominator would be 12. So this would be like 2 pi 12ths plus 3 pi 12ths in both cases. So if I multiply 3/2 times 6, That gives me 18/2 or 9. And then when I add these together, I guess I don't need the bracket, but if I add 2 pi/12 and 3 pi/12, that gives me 5 pi/12. And so if I add those, that'll also give me 5 pi/12. So that's all you need to do. And again, you could just use regular parentheses instead, because since we don't have any inside quantities, it's fine. Okay. So now let's look at dividing complex numbers. The idea is what we would do here. So when we're dividing complex numbers, we're going to take the moduli and divide. R1 divided by R2. Any guesses what we would do to our arguments? If you said subtract, you're right. We would take θ1 minus θ2. Okay. So in these cases, we would divide the moduli and subtract the arguments. Okay. All right, so in this case, we have, in example 5b, 9 times the cosine of 20 plus I sine 20 degrees divided by 5 times cosine 75 degrees plus I times the sine of 75 degrees. So we're dividing these two complex numbers. So first I would divide the moduli, so I would take 9 and divide that by 5. And now what I want to do is subtract 20 degrees minus 75 degrees to find what the new theta value will be. Okay. And we can see when we find that theta value that it ends up being negative 55 degrees. Now, one thing is we want to also use our other properties. We usually don't like having like a negative angle in there. We want it to be a positive angle. So here we can use the even and odd properties to kind of help us out. And remember that when we use the, for the even and odd properties, cosine is even. So that means that the cosine of 55 degrees is going to be the same, of negative 55 degrees is just the same as the cosine of 55 degrees. But since sine is odd, the sine of negative 55 degrees is like this, the opposite of sine of 55 degrees. So I'm going to transfer that negative up front. And then that would be the best way to write our final answer. Yes, I would want your degrees to be non-negative and something like that, okay? So again, from here to here, what we did is we used the even-odd identities. You need to make that note. Okay? Okay. Example 6. Anyway, that's the gist of it, okay, is to be able to multiply and divide these complex numbers that are in this trig form, okay? Example 6 kind of seems like a lot, but it's just kind of good practice going back and forth. Example 6, first of all, wants us to give the trig form of the complex number. Then we're going to perform this operation, which is division, using the trig form that we just used. Then we'll perform the indicated operation using standard form, which is like what we learned in Algebra 2, and then we'll compare our results together, okay? So the first thing that we want to do is to give the trig form of this complex number, okay? So to do that, that means that we want to give like our Z1, and we need to like give Z2, because there are two complex numbers that we're dealing with here. So let me use... Okay, here we go. So we're going to call this numerator Z1 and the denominator Z2. Okay, so let's just let's focus on Z1, which is 4i. If I wanted to find my r is going to be the square root of 0 squared plus 4 squared, which is going to be the square root of 16, which is 4. The other thing you could do is think about where 4i is going to land, and you can tell that's going to be 4 units away, okay? Also, when we think about where 4i lands, 4i means 0 on the real, and 4 on the imaginary axis. And so we don't have really a lot of work to do. We can tell right away that our theta is going to be pi over 2. And I'll use radians for this one. Okay. Okay, so that means that we can write what Z1 is. So because we have our R and our theta. So Z is going to be 4. And then we're going to have times the cosine of pi halves plus I times the sine of pi halves. Okay, so that's the first part. Okay, but there are 2 complex numbers that are being involved in this. We have Z1 and we have Z2. So now let's deal with Z2 down here. First, let's find what our R is. Our R is going to be the square root of -4 squared plus 2 squared. So that's going to be the square root of 16 plus 4. So the square root of 20, which is going to be 2 root 5. Okay, so this time not a pretty R. So I don't want you to think that the R values are always like pretty. They're not, okay? And so now we need to find our theta. And so we would take the tangent of theta is going to be B, which is 2, over A, which is -4. So that means that we have -1/2. Now, -1/2 is something that we've seen in our friendly numbers of the unit circle, but not for tangent, right? So what that means is that we're going to have to find our reference angle. And remember, when Mackie finds the reference angles, I always take the like the absolute value of that. Like I don't, like I always use like I always just take that tangent of inverse tangent of 1/2 personally. Okay, so that's my suggestion here. So again, I'm going to turn it into radian mode since I did my radians here. All right, and I'm going to take the inverse tangent of 1/2, or again, you could take the inverse tangent of -1/2. Take the absolute value. The idea is that your theta prime is about 0.464-ish, okay? And then we have to decide what quadrant to put that theta prime value in. When we think about where this is going to land, this is going to land in quadrant 3. And so, oh no, it's not. It's going to land in quadrant 2. Because they're not both negative. So -4 plus 2, I would end up here. Okay, so that's going to be in quadrant 2. So what I would do, because it's in quadrant 2, remember, is I would need to take pi minus that 0.464. Okay, so if I took pi minus that answer, that gives me, oh, what's happening? Oh, because I used that positive one, sorry. So I'm going to take pi minus 0.464. That gives me about 2.678, sorry. I subtracted a negative, so that was my issue. So my actual theta is going to be about 2.678. I knew that it couldn't be more than 3.14, so. All right, so now that I have my R and my theta, I can now write Z2 in, trigonometric form. So my R is going to be 2 root 5, and then I have the cosine of 2.678 plus I times the sine of 2.678, okay? And that's my Z2. Oh, this is not very pretty, I'm sorry. Okay. All right, so that's my letter A. Okay. So now what we'll do is we'll look at letter B, and in letter B, what they want us to do is they want us to divide the numbers now that we have them in that trigonometric form. And again, these aren't very pretty, so we'll just use a decimal approximation. So for letter B, I'm going to take Z1 over Z2. So I'm going to take this 4 times the cosine of pi halves plus I times the sine of pi halves, and then divide that by 2 root 5 times the cosine of 2.678 plus I times the sine of 2.678. Okay. So essentially what we want to do here is divide. And when we divide 4 over 2 root 5, do the cancellations here. So this would end up being 2 and 1. So I'd have 2 over root 5. And then I would need to rationalize. So there I end up with 2 root 5 over 5, if I'm rationalizing. And then in this case, I would want to subtract. So I would want to take pi halves, oops, and then subtract 2.678. And that gives me the cosine of about negative 1.107. And now I want to take pi halves, oh, it's the same thing, Sharon. So then plus I times the sine of negative 1.107. Okay. And again, we're just going to have a decimal form. I know that we could use the even and odd properties again. That would be beautiful. But since we're just going to compare it to what we get, let's just multiply these together. So I'm going to take 2 root 5 over 5 and multiply it by the cosine of negative 1.107. Okay. And so notice that this gives me about, this is an approximate too, this gives me about 0.400. Okay. And now I'm going to take 2 root 5 over 5 and then multiply by the sine of negative 1.107. And that gives me, if I round, that'll give me minus negative 0.800i. So that's what, if we divide the numbers in their polar form, that's what we end up getting for our letter B, is something like that. Okay. So then what letter C asks us to do, letter C asks us to find to actually perform, oh, let me code this. This is B. Letter C asks us to perform the operation using standard form, which I totally agree is like much easier. Like I totally agree with you. But again, this is just kind of practice going back and forth. So let's see what would happen if I did that. If I took 4i over negative 4 plus 2i, we know that a tactic is to use the conjugate. So I could multiply by negative 4 minus 2i over negative 4 minus 2i. So that gives me negative 16i minus 8i squared over 16, outer inner will cancel, minus 4i squared. So this negative 8i squared will really be like plus 8. This negative 4i squared will really be like plus 4. So that's going to be 8 minus 16i over 6 plus 4, which is 20. So I'm going to have 8 over 20, which is, divide by 4, 2/5. And then 16 over 20, which is 4/5. And I know that was so much faster. But the point is, they want you to see that really these are the same thing. Isn't 2/5 0.4? Isn't negative 4/5 negative 0.8? And that's what they just want you to I guess just to trust them now, trust these mathematicians now, that if you didn't believe them, even with the trigonometric explanation, that look, these really are equivalent to each other. Okay, so again, as far as like stuff like this, nothing that crazy. Usually if we were multiplying and dividing complex numbers, I would just have you leave it in that trigonometric form. I wouldn't have you turn that into the standard form. So, okay, that's it. You guys, welcome to 6-5. Have a great one.